In this video, we'll examine Prim's algorithm, which takes a graph that has weights on the edges as input and gives as output a minimum cost spanning tree. So if you've seen Kruskal's algorithm, Prim's algorithm gives the same output, but it just kind of goes about it a different way. So for Prim's algorithm, we need a starting vertex, and then we kind of grow the tree from that vertex. And at each step, we have some vertices that we've visited and some vertices that we haven't visited. And we examine all the edges that connect any visited vertex with any non-visited vertex. And out of all those possible edges, we pick the cheapest one each time. So each step grows the tree by one extra edge and vertex. Okay, so let's run through this example. To start Prim's algorithm, we're going to need a starting point, and that has to be given. So we'll just say we're going to start here, just to pick one. So again, we have visited and non-visited vertices, and we examine the edges in between those types of vertices and pick the cheapest one. So right now, the only visited vertex is the one that we chose to start. And then the edges that connect visited vertices with non-visited vertices are the ones that connect anything to this one vertex. So I have weights 2, 8, 17, and 23. Since 2 is the cheapest of those, I pick that, and now this vertex that I just added becomes visited. So now I have 2 visited vertices, and this is the part where I repeat step 2 until I have a spanning tree. In other words, until every vertex is visited. So okay, now edges between visited and non-visited vertices are 23, 17, 8, 6, 8, 10, 10, and 17. So I have to look at all these weights and pick the cheapest one. So 23, 17, 8, 6, 8, 10, 10, 17. 6 is the cheapest. So now that vertex is visited. And at each step I just repeat the same thing. So I have 23, 17, 8, 15, 19, 5, and all of these. So 5 is the cheapest one. So I'll add that. Now that's a visited vertex. So at each step I just scan and pick the cheapest one. So it looks like I have a 7 here, and that's the cheapest one. I wouldn't want to consider this 8, even though it wouldn't be the cheapest, because that's from a visited to a visited. So I add this 7, and now I still have all these edges to consider, but also I have a 22, a 7, a 2. The 2 is the cheapest, so I add that in. Now that's visited. And it looks like this 3 will now be the cheapest. So that one's there. So let's see, we have a lot to consider now. There's an 8. Yeah, the 8 is the cheapest. So this is the first one that is a little more interesting, because all we've done so far is just kind of follow this path through. But now we see an example where you can also add edges to vertices that you visited a long time ago. Okay, so it looks like I have here's a 12, maybe that's, no, there's an 11. But there's a 7 here, so actually I should have added this 7 before I added this 8. So sorry about that. This was added out of order. It didn't actually affect because none of these would have been added before, but yeah, that should have been the other way. Okay, let's see what we have. So now I'm kind of narrowing down. I have to add one of these 4 vertices, so I can kind of focus on which ones I need. So there's an 11, 12. To get here, I have an 18, 12, and 21. And to get this one, I have an 11. So I'm at a point where I need to make a choice. because the cheapest one is 11, but it also occurs here. And I can choose either one. There's no way to make the choice here, so I just break the tie, and I'll just add this one in. So I've used that 11. So everything over here is kind of covered. So it's got to be one of these three vertices. I have a 12, 18, 21, an 11, which probably is going to be it. And there's a 12 and a 23. So that's the one that I choose. Now I consider these up here. So I have this 8 that I should choose. And then finally, this is the last vertex, so I only have these three edges, so I pick the 12. So unlike Kruskal's, I don't have to check that the graph is connected, because at each step it's connecting back to the already connected part. All I have to make sure of is that I don't create cycles, but the fact that I don't choose an edge that revisits a previously visited vertex, that kind of takes care of it for me. So one of the benefits to Prim's algorithm is it's fairly straightforward to run. You don't have to check that you're creating cycles or disconnecting the graph, because it stays that way the whole time. And actually it turns out that you end up with a minimum cost spanning tree. So we found a spanning tree, and it is minimum cost, and the actual cost of the tree can be computed by summing all of the costs on all the edges in the tree. So if we just kind of follow this along, we'll start here, and we have an 8, 11, a 3, 2, and then we have a couple of 7s. We have this 11 here, and a 12 and a 5. We have a 6, a 2, and an 8. And since we have a lot of edges here, I just want to make sure that I got them all. So I'm going to count the number of weights that I have. I have 12 weights. Let's count the number of vertices. 13 vertices, which means that a spanning tree should have 12 weights. It's one fewer number of edges than the number of vertices. And so this is my cost. This is the cheapest cost for which you can cover this graph in minimum cost spanning tree. It's the cheapest cost. Not necessarily a unique graph. There could be other spanning trees of the same cost, but this is the one that Prim's gives, given some of the choices that we made along the way. So that is how you run Prim's algorithm.